Okay, yes, the recording has started. So on Sunday, we start talking about packages and how we can design packages. And we looked at the concept of, how basically we can develop package designs in a better way. And we discussed that, we have to focus on the concept of package cohesion, which means that, package should be cohesive in nature. And for that, we looked at three principles: the common closure principle, the common reuse principle, and the reuse release equivalence principle. And then, today, inshallah, we'll focus on the coupling principle, the package coupling principle. And again, we have three principles with us, which are the acyclic dependency principle, the stable dependency principle, and the stable abstraction principle. Now, before I move on and start talking about coupling, I think I explained to you guys your section, but to recap very quickly and to make sure that everybody is comfortable with the concept and what exactly we are doing here. Uh, you know, Let me start by very quickly recapping this cohesion and coupling concept in general, and then we can always go on, inshallah, and look at these three principles for today. Just to very quickly recap, remember, in a system or for a system, you will have many classes, right? And these classes, of course, will have inheritance and association relationships and so on and so forth. Now, the idea is, this is your UML package notation. So idea is that you somehow need to group related classes together into a package. And maybe, this could be another related classes, and you can group them together into another package. And you have a third package, and these three classes related together are packaged here. Now, how they're going to be related? Was the first question, and this focused on cohesion concept. That these classes, you are moving them together or you're putting them together in a package A, for example, they should be somehow cohesive. They should have some kind of relationship between them. Cohesiveness means they should be somehow together. There should be a reason for them to be together. They should not be random. And we looked at three principles. One principle number one was common closure principle, which means that the classes are going to be changing together. You're going to put them together in one package. On the other hand, the other one you had was the common reuse principle, which was all about that these classes you're going to put them together in one package because you tend to reuse them together. And we also looked on Sunday that these two concepts, the CCP and CRP concepts, are mutually exclusive. In other words, they are kind of competing with each other. And we discussed this on Sunday as well, that usually when your system is still going through a lot of changes, it's better that you package your systems in such a way that you follow the CCP principle, which means these classes which you're putting them together in a package are are the classes who are changing together. And then when the system will become more stable, you can always refactor your packages and apply the CRP principle to basically make it more feasible to use. And of course, the REP, or the reuse release equivalence principle, was an extension of the CRP. In other words, that this idea is all about that these packages you are creating, they should be based on reuse on a release level. This means more like a plugin, that this package becomes more like a black box. This whole thing will be reused as a package in other system. This is what we discussed on Sunday. Any questions on this before I move on to the next or today's concept, which is all about coupling? Everybody seems to be comfortable, right? Okay, alhamdulillah, I think so. Now, the coupling concept is just another very important related concept here again. See, these classes I'm showing you with X is just just as a concept. So these classes, of course, have associations between them as well, right? This means when you're going to move them to packages using the cohesion principles, they will still have relationships between these classes across packages, and as a result you will start having these relationships or dependencies between packages. And the whole idea of package coupling is that you want to minimize or reduce the interdependencies between packages, right? So you try to improve the cohesiveness of a package, and you try your best to your best abilities to reduce or minimize the coupling between packages. And how we do it? We have these three principles with us: the acyclic dependency principle, the stable dependency principle, and the stable abstraction principle. Again, everybody is comfortable about cohesion, because if we have this concept clear, then it will be a bit easy for us to look at these principles in detail. Any concerns? Otherwise, a few show of hands will give me a bit of confidence today. Thank you. Thank you very much. Okay. Now let's move straight to their concept. I think it was here. Okay. So principle of package coupling. The whole idea is, as I said a minute ago or a few minutes ago, that applications tend to be a large network of interrelated packages like this. They tend to have a lot of relationship between them, and the relationships between packages are there because the classes which compose a package have relationship with other classes, which is very natural in a typical application. Classes will have associations with other classes, and so on and so forth. So, these relationships are very important, and they are there for a reason. All we are trying to do is, when we are packaging them, the classes into packages, we are trying to make sure that somehow we minimize the relationships between the packages or dependencies between the packages. So we can have something called acyclic principle, dependency principle, right? As I said, we can apply this principle to help us improve the package coupling perspective. We can apply the stable dependency principle as well to again improve the package coupling or satisfy the package coupling principle or the stable abstraction one. So let's look at the first one, which is the acyclic dependency principle to begin with. What's an acyclic dependency principle? It says so that the dependencies between packages must not have cycles. So when the packages have dependencies between each other, we should somehow avoid cyclic dependencies between the packages. Now, let's look at a simple example. I'm already telling you that this diagram does not have a cycle. Now, if I have to release protocol package, what else I will have to release?
A common error, I think.
And why common error? Of course, you're right, absolutely right. But why common error?
Because it depends on protocol.
Yeah,
because
it depends on protocol, right? So if I have to in other words, we will have to make sure that if I want to release the protocol package, I will have to also release the common error package as well, right? Because it depends on it, right? Now, everybody's comfortable with this?
Yes.
Yes.
Okay. Now let's look at the case which is the more interesting and the one we are trying to understand, which is the cyclic one. So now in this case, we have a cycle here. Right, that common error package depends on the GUI, and then things can keep going. So now if I have to release the protocol, what will happen? What packages I will have to release as well?
All of it.
All of it, right? And why is that?
Because of the dependencies between the common error and the GUI.
Yes, because of this
And the
dependence,
GUI, yeah,
GUI on communication and analysis and all of that stuff, right?
right.
So, so the whole idea we're trying to do here is we're trying to say that let's not have cycles in our dependencies, and which is very obvious from this case that since there is a cycle here, as a result, you as a software engineer would have to build and test, so if there's a change here, if you release here, this one, you will have to go and check common error, you will have to check GUI, you will have to check communication, you will have to check modern control, you have to check analysis, you have to check database, pretty much everything. And this is not advisable, correct?
Yes.
Because there's so much coupling between these packages now that a small change in one package is actually means changing the whole thing, just testing the everything. It's not modular at all from that perspective, right? Now, before we look at how we can break these cycles and all that kind of stuff, we need to understand why we have this dependency to begin with. What could be a reason that we have this dependency?
Maybe we didn't apply the first rule correctly, the cohesion principle.
Absolutely, that's, as Ali said, absolutely, that's quite possible that we didn't apply the way these packages were created, right? Absolutely, that's quite possible. Now, if that is the case, that we didn't apply the cohesiveness principle here, this means we have some classes here, right? So this common error has a bunch of classes which are actually depending on the GUI classes, right? Or the classes within the GUI package. Because remember, these packages at the end of the day consist of classes. So we may have a group of classes when we applied the cohesiveness principle, or for some other reason, it contains certain classes which are actually depending on the classes within the GUI. Now, what could be the solutions there? What do you think? What could be the solutions there?
Move these classes to the GUI and delete the dependencies.
Maybe this is one solution, right? But then again, remember, when we're going to do this, we still have to maintain the cohesiveness as well. Remember, right?
Right.
So yeah. So this is a valid solution. I mean, because here we're talking about a very hypothetical situation here, right? We don't have the real classes in front of us. But that's a valid solution. Yeah. So there could be many other solutions. Some other solution comes to mind.
Maybe take this class and make another package and make a dependency between GUI and the common error to this package. Maybe.
Absolutely. Maybe. Why not? Absolutely. Why not? All right. Anybody else would like to share some thoughts on this? Okay, so let's look at some examples. As Saul said, one way is basically, as you said, split it, right? The classes which are actually causing this dependency, move them into a separate package and call them message. In this case, we're just calling them message manager or something like this. And we invert this, dependency. So basically, the classes that common error needed are pulled out of the GUI. So the classes it needs, the common error, for example, needs from the GUI, you pull it out and you create a new package called message manager. And then both the GUI and the common error will start depending on each other on this new created package. Now, if I have to change a release protocol, do I have to change everything?
No.
No. What will the things I will have to change or check or test?
Common errors and manager messages.
Exactly. Exactly. All right. So one solution is to create new packages to split them, and since there was a dependency between, so this means since there was a dependency between common error and GUI, that meant that there were certain classes in common error which were depending on classes in GUI. So we pull those classes out, create a new package, and as a result, we break this cycle. This is one solution. As I said, there could be many solutions. Another possible solution is this, and let's look at this example. Remember, as I said, in the beginning, that the relationships or the dependencies between packages are there because the classes within them have dependencies, right? So why there is a cycle in this case? Let's look at the top one. Why there is a cycle in this case? So why there is a cycle between package A and package B?
Because A depends on X and Y depends on B.
Exactly. So there is a cyclic dependency between package A and B, and the reason actually, when we investigated, we realized that actually this dependency is there because class A of package A depends on B, class X of B, and similarly, the vice versa. So we have a cycle, and the cycle is because class A depends on X and class Y depends on B. Now, how we can break this, right? Now, I'm just also already showing you the solution here, by the way. Now, one way of breaking this, and this is, by the way, a magic solution, to be honest, you will see this solution now again and again popping up, this interface concept, all right? That the way we can break this cycle is that, for example, we break the cycle by inverting the dependencies between Y and B. And how we can do that is basically by adding a new interface called BY. This interface has all the methods Y need, right? And Y uses this interface and B implements it. Is this clear? Is this solution clear? What we have done here?
So it's
Can
gonna
please
call
repeat?
B.
Yes, one by one, please go ahead.
So it is going to call B, but through the interface.
Yes. So Y is gonna call B, but it's gonna through the interface.
Uh,
It's a magic solution. It's a silver bullet. This interface. Whenever you will have these kind of issues in your design, you will see it, inshallah, as I'm going to move to classes now, that whenever you are trying to satisfy certain class design principles, and you will see them again and again popping up in design patterns as well. Is this point clear? Would you like to take a moment and read this bullet point, please? Because I want to make sure everybody's understand what we did it, how we split this one. Yes, Jawad. Yes, Jawad. Go ahead, please.
Uh, can we do interface in the other package A instead of package B?
Somewhere
It
here.
depends.
Somewhere
Okay.
here. Yeah, why not?
Yeah.
Why not? Yeah, this is just an example. Absolutely. Yes, Abdul Majid, you're gonna say something?
the interface being in package B, is this satisfy the cohesion principle? Or?
Okay, okay. Uh, yeah, no, of course you can always move this interface here. It doesn't matter, right? Yeah, so that's a good observation. Uh, to remember, when we're gonna look at these whole package diagrams, we're gonna try and come to an optimal solution. They are all competing with each other, this coupling and cohesion principle, right? So basically we try to come with a solution which gives us a decent cohesion and decent coupling, right? So yeah, one can always move the interface to the other package from a cohesiveness perspective. Nothing wrong in it, absolutely. So see what are the two different solutions and you can always think of many others. By the way, these are the two common solutions. That if you have cycles, one solution is to try to split the packages. Okay. And other solution is that start creating interfaces. And with the help of interfaces, you segregate the internal dependencies, the direct dependencies, and as a result, anything which is behind the interface becomes a black box. So any change behind the interface will have no impact on the ones who are using those interfaces. Correct? And inshallah, you will see this again and again in the design patterns and other principle class design principles as well. So far, so good?
Yes.
Okay. Now let's move on. So this is basically, our acyclic dependency principle, that don't have cycles between packages, avoid them, remove them. And we know now that one option is to have interfaces, the other option is to create new packages. Let's look at the second principle for cohesiveness, which is all about stability or stable dependency principle. So like your special focus here now, because this is slightly a different concept. So what we're saying here is that the dependency between the packages should be in the direction of the stability of the packages. In other words, what we're saying here now is that only depend on the packages that are more stable than it is. So if I'm a package A, I should depend on the package B or that package which is more stable than myself, right? This is the idea, the fundamental idea behind this stable dependency principle, that should depend on packages that are more stable than it is. Of course, the question is, what is stable? What is the meaning of a stable? How I calculate stable or stability? So, of course, there are so many different understandings and meaning of the word stability in software engineering, especially in the software matrices. I'm just going to use one example here because this is not a software matrix course or a quality course. Inshallah, for the next generations, we have a course called 439, which is being introduced as a new core course. Inshallah, the students will focus and learn how these quality measures are defined and what are these ones and how we can really define them and use them. But here in 316, I'm just going to use one example of these stability metrics or one example of how we can calculate it. So in our case, in our context of discussion today, we are not referring to stability in terms of frequency of change. So we're not saying that frequency of a change is stability. This is another way of measuring stability. I'm not focusing on that. Right. So stability in this context has nothing to do with the frequency of the change. What is the meaning of stability in this principle is that we roughly means that a package is stable if it is hard to change. And we say a package is unstable if it's easy to change. Okay. If I have to recap very quickly, we are talking about stability dependency principle. And we are saying that as part of this principle, a package should depend on the packages which are more stable than myself. And then how I calculate stability, we are saying that stability in our context means something which is hard to change. So a package which is hard to change is stable, and a package which is relatively easy to change will be unstable. And the principle says I as a package should depend on a package which is harder than myself to change. Of course, still I have not defined how we really measure stability, right? But this as a concept, it's starting making sense. Hopefully with the example, it will become well more clearer. So stability in our context means hard to change and instability means easy to change. So let's look at this. In other words, we are saying what? That the software package is difficult to change. In other words, they are stable if it makes a lot of other software packages depend upon it. Right? So we will say that a package will be called stable package because it's hard to change, right? Because in our definition, stability means hard to change. So we'll say a package is stable because it's hard to change because there are a lot of other packages which are depending on it. Why? It's hard to change if there are so many other packages depending on it.
Again, doctor, can you repeat the question?
Yes. My question is everybody's comfortable with this so far? Stability means hard to change, right?
Right.
And instability
Right,
means easy to change. So I'm saying, in other words, I'm saying that a package, a software package which is difficult to change is the one on which a lot of other packages are depending. Why it's hard to change? Why that is stable package according to our definition?
I think it's a core package like GUI or maybe system. Maybe.
Yeah, it's probably the system or the core of the system, definitely. But why it is hard to change? Because I'm saying a package is hard to change because a lot of other packages are depending on it. Why is this? What is the case?
Okay. Because if you change it, we'll change the other packages, or it will affect the other packages.
Exactly. Right. So if a package, a lot of other packages are depending on it, of course it's harder to change because it has rippling effect. Right. So in other words, a package with a lot of incoming dependencies is a very stable one. Right. Because if a lot of other packages are depending on it, then if I'm going to make a change on this one, then all the others will need to be changed as well. And our definition is that stability is a package is called stable if it is hard to change. I think it is clearer now, right?
Yes.
Anybody who's not sure, I can repeat this because if we understand this, I can move on to the next one, to the next slide where we actually calculate it.
Doctor, what about easy? We saw the situation where it's hard to change. If there is many packages depend on it.
Correct.
But when is it easy to change?
Easy to change will be the other way around. Absolutely right. Which will be that no one is depending on this package, right?
Yeah. Okay.
All right. So that will be the other extreme.
Yes.
So that will be highly unstable in that in our definition.
Yes.
Okay. So
Doctor, sorry, could you repeat that if a package does not have any dependencies,
yes,
it will not be stable?
It will be not stable. Yes.
So it's a bad thing, right?
It's not a good or a bad. Yeah, it's not a good or a bad thing in a sense. It's that our principle says that I as a package should depend on a package which is more stable than myself.
So when you have more dependencies, you will be more stable, or when
Yes.
you have
Yes.
more packages depend on you. So
Yes.
okay.
Yeah. So in other words, I'm a package and a lot of people are depending on me. So it's more stable because if I change, a lot of things have to be changed in the other packages as well, right?
I got it.
Yeah, and hopefully this will
Yes.
become even more clear with this example. So let's say I'm saying X is stable. Why?
Has more packages depend on it. Three
Yeah,
packages.
so there are more
in
packages
exact.
depending on it and no one is depending on X.
Right.
right? So in this case, we say that this package X is more stable or is stable with relative to these other three, because it has many incoming. This means this incoming means these packages are depending on it. This package is depending on them, right?
So, Doctor, I have one question. If we have two level of dependencies, like if you have one package that X in this example has three dependencies or three packages depend on it, then these three packages has three packages also depend on each of them. So
Like on
does
top
that
of,
increase the stability of X
yeah, on
package?
the top, yeah, on top of it, right? Something like this, right?
Yes, like hierarchy.
Yeah,
Hierarchy.
hierarchy. Yes,
Exactly.
yes,
Yeah.
yes, 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 yes. Now, just bear with me. Inshallah, I'm going to define a formula very shortly, right? And this will, inshallah, answer the question here. Okay. We'll come back to this
Okay.
question. Valid question. We'll come back to this question very shortly. So we say X is stable because, as our principle, X is stable because it has a lot of incoming dependencies, but no outgoing dependency. While on the other hand, we're saying Y is unstable, which means easy to change because no one is depending on me on Y, right? And these packages are depending on Y, right? So there are a lot of outgoing there, but no one is depending on Y. Hence, if I change it, khalas, that's no problem, right? So far, so good.
Yes, Doctor. Yes.
Okay. Alhamdulillah. Now let's look at this important question about how I calculate a specific one, and especially about this hierarchies and how overall. So how I calculate a stability of a package is that we have something called stability matrix. It's a very simple matrix, and we calculate a stability of a package. Important point to understand, of a package, not the whole system. So stability of a package as follows. It's a CA divided by CA plus CE. Now, what is CA? CA is called afferent coupling, and it actually means what? It means the number of classes outside the package. So if I have this package, so the number of classes outside the package that depend upon the classes inside the package. In other words, the incoming dependencies, right? This is CA. What is CE? A is there for the afferent one, right? Efferent one for CE is what? It is the flip side of it. It's the number of classes outside the package that the classes inside the package depend upon. In other words, the outgoing dependencies. Take a moment to read these two. Take a moment to understand them. So I like you, all of you guys. Of course, I can't see you guys, but I like you guys to maybe take a minute and read it. Everybody's comfortable with this? Okay. Now, what do you think? What will be the range of this one? What do you think? What will be the range of this one? The value of S for a package?
0 to 1.
0 to 1, absolutely. Right, so the range will be between 0 and 1. Now, when it will be 1, or let's start with the 0. When it will be 0?
When it will be
zero,
very stable.
Yeah, when it will be the value of, when the value of S will be 0?
When it's
when
unstable.
all the classes depending on the package is zero, or all the packages depending on the
depending on the package or zero.
Another let's look at this from the CA and CE value. So what will be the value of CA for us to have 0?
0.
0.
So this should be 0, right? So this means what? There are no incoming dependencies, correct? For a package, for us to have a CA value equal to 0, this means there are no incoming dependencies, right? Now, if this is 0, so if I have a package where no incoming dependencies are coming, but what if I have CE equal to 10? What will be the value of the stability of this package?
0.
Will still be 0, right? So it doesn't matter if it is 100, 10, million, does not matter, right? So we will have a value of 0 for a package if there are no incoming dependencies, correct? Now, what if, since we were talking about no incoming, what if I have no outgoing as well? What if this is also 0?
Invalid.
Invalid, right? And does it make sense that it will be invalid from a package perspective? What that will mean? No incoming, no outgoing.
No.
It means it is not stable and not stable.
It cannot be calculated, Doctor. That case.
That's undefined. This is undefined, correct? Now it's
It means
undefined.
the package work alone.
Sorry?
It means the package is alone without any relationship.
Yes. Jazakumullah khair. This means package is alone. This is only one package, right? No incoming, no outgoing, right? Then I don't even care about stability, right? Correct?
Yes.
Yeah. So everybody on board with me here, right? So that's so this is okay. Now when it will be 1?
When outgoing is 0.
When outgoing is 0.
And the incoming is non-zero.
Is non-zero. So it is 1 or million, does not matter, right? It will always become 1. So far so good, right? So in a nutshell, our stability for a package will have a value between 0 and 1. Of course, if there is no incoming, the value of S will be 0 and we will call it package is unstable, which will mean what? Easy to change or hard to change?
Easy to change.
Easy to change. Because there are no incoming. This means nobody depends on me, right? So I can go on and change it. While on the other side, if there are no outgoing dependencies, this means, you know, the value of S will be 1 and package is stable. This means it's very hard to change. And of course, by hard to change means a lot of people are depending on me, but I'm not depending on anybody, or relatively, I have a better S value, right? So these are the two extremes. Of course, you can always have a value because of the hierarchy. Because of the hierarchy, you can have a value, or in other words, because of that, you will have a value between 0 and 1 as well. Now, let's go back to the question of hierarchy. Now, based on this formula, if I want to calculate the value of stability of a package X, has the value of these one have any impact according to this formula?
No.
No. So according to this calculation, it has no impact of hierarchy, does not have any impact on this, right? Now that's another question, whether that's a good formula or not, right? Whether I should consider that further level of hierarchical dependencies or not, right? That's another debate. And of course, I'm just using one simple case here for us to look at it. Of course, I mean, since we talked about it, it's always good to look at you know, the levels of hierarchy as well, and that's why we have other formulas. By the way, there are other concepts like centralities, and they're within centralities. They are like degree centralities, and there are other centrality concepts which basically, you know, give us better reflection or the number better reflects, the relationships. But that's beyond our discussion in 316. Inshallah, next generation 439, they will talk about this in detail, right? So far, so good.
Yes.
Yes.
Okay. So if I have to rephrase now, the whole idea is we went through this whole exercise is because we are interested in the stability principle, right? So in other words, I said in the beginning that stability dependency principle says that I as a package should depend on a package which is more stable than myself, right? So now because we know the formula, we can say this, right? We can say that this principle is actually saying to us what? Depend upon packages. So if I am a package A, I should depend on a package whose S value is higher than myself. Correct?
Yes.
Right? Because my rule is I as a package should depend on a package who's more stable than myself. This means when I say they are more stable than myself, this means their value of S should be higher than mine.
Doctor, could it be that S value equal between two packages?
Well, yeah, it's quite possible. Theoretically, yes,
Okay.
it's quite possible, but that will be very interesting. This means probably they have no relationship. That will probably what will happen is that in a whole system, two packages may have the same S value, but then probably there is high probability that they don't have any relationship between them. Direct relationship.
Yeah.
Yes, quite possible. So the software that encapsulates high level of design of S should be placed into a stable package. So in other words, what I'm telling you guys, this whole exercise we did is to so this is like a conclusion, a nutshell of our discussion here is that, because a package whose S value is 1, right, whose S value is 1 actually means it's very stable. This means very hard. This means a lot of packages are depending on it. In other words, I should put the core part of my design, which is not going to change into those packages. Okay. While on the flip side, the things which are going to change a lot or which are going to be flexible, I should put them into packages whose S value is 0 or less, right? Because this means a value of 0 will mean nobody depends on it, right? So hence I'm easy to change. Is these 2 points clear? Or I can repeat it. This is a critical observation of the whole discussion.
Doctor, could you repeat it just one more time?
Yes.
This last point, please.
Okay, sure. Let's start from here because that's a good starting point. We are saying since we know the stability of each of the package, and our principle was that I as a package should depend on another package who's more stable. In other words, we are saying that organize them in such a way from a coupling perspective that I as a package, I should depend on the package whose S value is greater than myself because of course they are more stable than myself. That means they are more harder to change than myself. So if I have a bunch of classes who are very core to my system and they are very stable and they should not be changing a lot, right? Or I'm not going to make them change, then by intuition, it's clear that high level design part of the system, the things which are not going to change, I should put them into stable packages whose value of S is 1 or close to 1, because we know that since I'm going to organize them I'm going to organize these packages based on their stabilities, and I'm going to make sure that I organize them in such a way that that when I have a package of value of S1, which means it's highly stable. This means it's very hard to change. So I will easily try to put those classes who are, I'm not going to make any changes to them into those packages. While on the other hand, the flip side is that a package which is value is zero or close to zero means they're very easy to change. This means, they're not a lot of packages are depending on it. Hence, the classes, the part of the system I want to change or I know needs to be flexible, I can put them in those packages because I'm going to organize them in such a way that a package depend on the other package in such a way that they depend on each other on higher S values.
Yes, it's clear.
Good, alhamdulillah. I think it's what 10:50 now, right? Almost right.
Almost, yeah.
Almost. So I think we'll
Yeah.
stop it here. I'll look at these examples and I'll try to explain how this is breaking it and what are the solutions. Of course, as I said, interface is going to be a magic solution, inshallah. So whenever you're going to be stuck somewhere, use interface. You won't go wrong. It's just my rule of thumb. Okay. But we'll talk about this inshallah on Thursday. We'll stop it here. Let me stop the recording and take the attendance.
Yes.